Hello everybody. Thank you for joining us in the next and ContinualAI seminar session. Today we have the pleasure to host Vivian Madan, who is going to present his recent paper published as an oral at iClear 2022. So I read the reviews and they were all very happy about the paper, and I think this is going to be a very nice talk about unsupervised continual learning. So an emerging topic, a very fast growing one, but also one in which we need new ideas and new results and insights for future work. So I really hope Vivian will give us lots of these. And so without further ado, let's start, and Vivian, the stage is yours.
Thank you for the great introduction, and thank you for having me. Let me start sharing my screen. Can you see the slides?
Yeah, perfect.
Good. So, yeah, I'm excited to present our work titled Representational Continuity for Unsupervised Continual Learning. I'm a first-year PhD student at NYU, and this work was done with my amazing collaborators Jaehong Yoon, Yuan-Chun Lee, Yung-Shin Liu, and Sung-Ju Wang. So, the motivation of this work that we started with was that you have a large amount of unsupervised data which is actually generated every minute of the day. So if you're just surfing the internet, you are technically having 500 hours of content which is uploaded on YouTube, which we are streaming on right now. There are like 695,000 stories shared on Instagram every minute. But a large amount of this data is unsupervised because it's hard to label this every minute of the day data generated in such a large amount. So our motivation was if we can somehow take a step towards this of using this unlabeled data directly and learn it on the fly. Parallel to this, there has been a large amount of progress in machine learning, which is data driven. So we have a large amount of data sets like ImageNet, or Visual Genome, or COCO for object detection, or VQA, or even the YouTube 8 million dataset. So it's harder to collect these large datasets in just one go, because if you have to collect so many data points, you need annotators to annotate in such a huge amount, and it's not an easy task at all. Also, feel free to ask questions in between if you have any, or we can also take them in the end. So, as I said previously, it's not easy to collect such a large data set in just one go. In most of the cases, you start with a small data set, and the data set is normally dynamically growing. So let's take an example here. The figure that you see on the slide is, let's say we had 22,000 classes of cars initially. And as the technology grew, the number of classes have grown also. So now maybe we have 1 million classes in the wild, and initially, the dataset which was created with just 22,000 classes has now expanded to such a huge size. And ideally, what we want is that with every small growing amount of change, we want to update a model which has been learned to classify these classes. Thus, we want to learn or continually learn on the arriving data while preserving the knowledge that we have previously learned. So you might be aware of continual learning as one method to do that. So in continual learning, normally what you want to do is that if you have some set of tasks, then when a new task arrives, you want to update your model to learn on that new real life class or task, but you also want to preserve the information or knowledge that has been learned previously. And often the problem that arises here is catastrophic forgetting, where the model forgets the knowledge it has previously learned. And there are various methods to prevent catastrophic forgetting, but many of them are on the supervised setting. So this work is centrally focused on working on the unsupervised setting and preventing the catastrophic forgetting problem. So as I said earlier, annotation is not really easy. So that's one of the great motivations that we had, that you cannot just annotate on spaces where it's actually hard. So for example, if you see this figure on the left, normally you have to annotate the bounding boxes. You have to have the corners of the bounding box, which is actually a harder task too. And when you take a step further and you go to the video input space, then there can be various kind of annotations that you could do. Maybe you want to annotate on the pixel space, maybe you want to annotate on the frame space. So annotation in these kind of things is actually a extremely hard task. And also in some cases, it's not easy for a normal human being to annotate. Like you need some expert knowledge. For example, if you see this figure in the right, it's an example of retrosynthesis. And in these kind of examples, you often need experts. And having experts is also expensive and time consuming. Therefore, it is extremely important to learn the representations continually on these unlabeled data streams. So the objective that we have in this work is to come up with scalable unsupervised continual learning representation. So the expectation that you have there is that if you have a self-driving car, for example, which is here, maybe it's learning on a set of frames or on a set of images, then when it has encountered a sudden new frame, you want to update its model to take into account the knowledge which it has gathered from the new frame without forgetting the knowledge it has learned previously. So before we started this work, there was this work called as CLAI, which took a step in this unsupervised representational learning setting. And what they actually did was they aimed to learn task-specific representations on top of like shared parameters. But this method was actually quite complicated. Like they used mixture of Gaussian models during task inference, and they had a generative replay and also a dynamic expansion, which they used for preventing catastrophic forgetting. The major limitation of this work was that it was not really scalable. So if you see their experiments, they were limited to like low resolution tasks. And the problem there was because they required task specific representations. So when you're scaling to large number of tasks, it's hard to scale this method. And it's also not really applicable to the real continual learning benchmarks that we normally have. So we wanted to fix this problem, and that's why we modeled this unsupervised continual learning problem framework. So take an example where you have a sequence of tasks, say U1 to U tau. Now what you want to learn is, you want to learn a feature extractor with the self-supervised loss, and you don't really have labels for any of these tasks. So what you can do is use different views or use different distortions of the unlabeled examples that you have and sort of minimize the distortion between those views or distortion using the self-supervised loss. But the problem is you cannot just do a trivial combination of like self-supervised learning and just learn it directly on this sequence of tasks, because you would have this problem of catastrophic forgetting. So the essential thing to do there is to revisit the representations learned on the previous tasks, just like we have it in the supervised continual learning framework. So you want to make sure that when you are on the task U tau, you want to revisit the representations learned on the previous tasks. And you could do this in various forms. So we attempt various methods which all the categories of continual learning basically. So in the supervised continual learning, you normally have regularization as one method, you have replay as another, and you have architectural expansion as another one. So we try to extend all the three basically to the unsupervised continual learning framework, and we show how we can actually do that. Apart from that, we also propose a new method called as Lifelong Unsupervised Mixup, which is an extremely simple method to prevent catastrophic forgetting, which I'll talk about more in a few minutes. And another thing to note here is that during inference, since you don't have labels, we use a KNN classifier for the evaluation. You could also do a linear network or have a linear classifier in the end, and you could fine tune that linear classifier for evaluation. But the problem there is that it takes some time to do that linear evaluation on each and every task. And also evaluating that, like using that during training, is a computationally expensive task. So we wanted to keep it as much close to the unsupervised framework as we could. That's why we chose the KNN classifier as a choice. And we do a range of quantitative and qualitative empirical analysis. We show that our method works across a range of tasks that we consider, and we also show that why it works. And in the end, the takeaway is that reliance on annotated data is not at all necessary for doing continual learning. So yeah, let's delve deep into the method now. So the first choice you might have is then why self-supervised learning? So the motivation for that was that representational learning have shown a huge potential these days. So they can basically learn the data on the fly, which was one of the motivations as I mentioned earlier. You don't really need the labels at all. And if you see this graph on the right, then many of the recent methods like Simpler, BYOL, or SWAV have attained great performance, and they have achieved better performance than the supervised baseline that we already have. So it was surprising to us that given the success of these methods, no one has done an attempt to do unsupervised learning in continual learning, because we know that unsupervised or the self-supervised learning can actually outperform supervised. So we were very curious to see, does this pattern also hold for continual learning? Is the self-supervised learning also more robust to catastrophic forgetting? What's happening in that space? So that's why we took 2 works to investigate that thing. So when I started this work, SimSham was one method which existed at that time. It was accepted as CVPR oral, and it was the most recent method at that point of time. And it was interesting because it does not require contrastive learning. So it's sort of a non-contrastive learning method. By non-contrastive learning, I mean that you don't really need the negatives to learn this network. The advantage there is that basically sampling the negatives is a harder task, because you need to find good negatives or you could have the collapse problem. And SimSham took a step in having a non-contrastive learning method working for representational learning. And to just give you a background on how it works. So for example, if you have an image, you generate 2 augmented views of that same image, say x1 and x2, you pass it through an encoder, and then you are minimizing the similarity across the 2 representation views that you have got. But the trick there is that you have to have a stop gradient operation across one branch. So it is essential to prevent the collapse problem. Otherwise, normally the Siamese network suffers from an output collapse, which you can see from this graph here. So if there is no collapse, your representations, if they are spread across a hypersphere with 0 mean, then 1 by root d should be the standard deviation of that particular channel that you are considering. If you have a collapse, then basically it just goes to 0, and if you use a stop gradient operation, you can prevent that collapse. And you can also see the results for accuracy. When you are having the collapse, it's just 0%, and when you don't have a collapse, it works pretty well. And this is the corresponding loss. So it's very simple. Is you just have a stop gradient operation across the other branch that you are using, and you get the gradients only from P1 or P2, or the predictor basically. And once we did that, then we found another method called as Barlow twins, which was accepted in ICML. And this was another non-contrastive learning method, which was our focus at that time. And for Barlow twins, it's a similar method that you use the images, you use the distorted images, but you don't use the stop gradient operation. So instead what they do is that you have your embeddings, ZA and ZB, you minimize the you find the cross correlation matrix between both these embeddings, and you have 2 terms in the loss. One is the invariance term and the other is the redundancy reduction term. So what they are basically doing is, in the invariance terms, you want to make sure that your diagonal is basically pushed to an identity matrix. That basically means that all the distorted embeddings should be similar to each other. And the redundancy reduction, what it does is that the off-diagonal elements should be pushed close to 0. And in that case, you want to minimize the redundancy across the various components of the vector that you have. So that was sort of a background of the 2 methods that we investigated. And moving to the limitations of these methods. So these were limited to the large amount of data. So if you have seen any self-supervised learning method, any basically that you consider, most of them just train on large, like ImageNet. And ImageNet is a huge data set to actually train on, and then they just evaluate on a few downstream tasks or the limited amount of labels for ImageNet. As I mentioned earlier, it's very hard normally to collect such a huge data set and train these self-supervised learning methods on such a huge data set for training on the downstream tasks. So that was another thing. That was a bridge between representational learning and continual learning that we wanted to construct, that you really don't need such a huge data to learn your self-supervised learning methods. You can start with a small data set and then keep on learning these representations as you get or collect more and more data. So starting with unsupervised structural regularization that we started with. So what unsupervised structural regularization, you might know about structural regularization, the supervised one. In this case, what happens is that if you have a task A and you are going towards task B, if you don't have a regularization, you would just drift towards task B, forgetting the knowledge that you have learned on task A. And ideally, what the structural regularization methods like EWC or SI, synaptic intelligence, do is they have a regularization term which minimizes the distance between the parameters of task A and the task B, so that you are lying some middle of the region. And it's very easy to adopt the supervised methods to the unsupervised ones. So we use synaptic intelligence in our work, which was sort of a successor of the PWC. And what you do is basically you learn the current task loss using the unsupervised scheme, and then you have the same surrogate loss which synaptic intelligence uses. And for the unsupervised loss, you can use either Shim-Sham, you can use Barlow twins, or you can use any of the current methods that you want to try. Then coming to unsupervised replay. So for unsupervised replay, we chose dark experience replay for evaluating the progress. We also have other methods like AGM in the paper. You can look at the paper for more unsupervised replay methods. But here I would give you an idea of how dark experience replay can be adopted for unsupervised replay. So let's take an example that you have an unlabeled current task and you have your unsupervised representations. And you have your replay buffer, which is basically also composed of the unlabeled data instances that have been stored from the previous tasks. Then since we are using dark experience replay, what you do is you take the logits. So you take the logits of your current examples and you take the logits of the replay buffer on the current network representations, which is f theta t passing x to it. And you just minimize the Euclidean distance between both of them. So one thing to note here is that the dark experience replay was actually using the logits for minimizing this distance, but since we are working in the unsupervised space, we do not have access to the logits. So basically they do not make sense. So what we do is we approximate or use an alternative to that by using the projector embeddings, and we minimize the distance between both of them. So it's not a very good approximation or an alternative that you could choose, but we show that even that works for us. So in the overall loss that you see is similar. You have your current task loss, and then you're minimizing the Euclidean distance between the unlabeled current task and the unlabeled replay buffer that you have stored. So moving to the next method that we propose. So we propose something called as lifelong unsupervised mixup, and the motivation for this work was that normally when you have those replay methods, like any replay method that you take, you basically have these regularization, hyperparameters that you have to tune. So this alpha, for example, is quite critical to get the performance on how your model should work, and there are many other such things when you're doing the replay buffer example. So we wanted to eliminate this and have a very simple method that you could just work on the fly, and it's very easy to implement. What we basically do is you have your unlabeled current task, you have your replay buffer, you mix between both of them. So you construct an interpolated set of examples, which is constructed by an interpolation of the current task and the replay buffer, and we call this as the lump examples. And then you just use the interpolated examples for your unsupervised representation. So you don't need the you don't need any of them. You don't need to find how much of the loss term that I need to use. You basically just use the interpolated examples and use them for training your self-supervised loss. And this makes it very easy to test things, and it's quite simple and easy and also effective, as I'll show you in the results. So yeah, that was about the methodology. I'll next move to the experiments. If anyone has questions do you want to ask, I can just proceed with the experimental settings. Okay, so let's move to the experimental setup. Then we evaluate on 3 data sets. Primarily, we use with SIPR10, which is a sequential version of SIPR10. And in this case, we have 20 tasks from 10 animals and vehicle classes. And we also use split SIPR100, which is sort of a scaled up version of SIPR100. And in this case, you have more variety of tasks. So we have 20 tasks in this case compared to just 5 in the SIPR10. And we also use split tiny ImageNet, which is a higher resolution, but we keep the number of tasks and the classes the same for this. And for evaluation, we use 2 metrics. One is the accuracy and one is forgetting. So accuracy is basically the average test accuracy of all the tasks completed until the continual learning of task tower. And we also use forgetting, which both of these are standard metrics. And in this forgetting metric, you basically have the average performance decrease between the maximum accuracy and the accuracy after the completion of training. And in both the cases, the accuracy is computed using the k nearest neighbor classifier, as I mentioned earlier. So yeah, let's move to the results. So moving to the evaluation, let's start with the accuracy first. So if you see the plots, then we have fine-tuned synaptic intelligence and DER for a comparison between SCL and UCL. SCL basically denotes supervised continual learning, and UCL denotes unsupervised continual learning. And if you see, the unsupervised fine-tune is far better than the supervised fine-tune, which is sort of very interesting, because normally if you see continual learning papers, many people don't really evaluate the fine-tuning baseline. They come up with fancy methods to prevent the catastrophic forgetting, but we show that just a normal fine-tuning baseline, if you see, just in the unsupervised sense, can outperform or get comparable performance to various state-of-the-art supervised continual learning methods. And similarly, if you see, unsupervised SI works better than the supervised one. For DER, it was interesting for CIFAR 100 that we observed the accuracy, and as I said earlier, it's not the best alternative that we came up with, so definitely there can be alternative things that can be tried. But for tiny ImageNet, we did observe gains, and with Mixup, we observed the best performance across all the data sets. And we also see the same trend for Barlow twins. So if you see with Barlow twins also, the unsupervised methods outperform the supervised methods across both the datasets, with Mixup giving you the best performance. Then moving to catastrophic forgetting. So if you see the catastrophic forgetting trends, then again UCL shows you significant gains. So in terms of numbers, you would see around 20% absolute gain across the supervised counterpart for fine-tune and SI. And interestingly, you see that all the DER did not help much with the accuracy part. It does help to lower the catastrophic forgetting. And Mixup again gets pretty good, pretty low forgetting compared to the other methods. And then similar trends were observed with Barlow twins. Again, unsupervised works a lot better than the supervised counterpart, and the same holds for all the methods. So this was the continual learning evaluation. The next thing we wanted to do was an out of distribution evaluation, and the motivation to do this was that normally in the self-supervised learning, you evaluate the performance on various downstream tasks. So instead of evaluating on downstream tasks, we wanted to see how much are these representations generalizable to various out of distribution tasks. So we picked 4 datasets depending upon the training dataset. So here I show the results for sequential CIFAR 100 model. And we take MNIST, FMNIST, SVHN, and CIFAR 10 as 4 OOD datasets. And if you see across all the datasets, most of the times unsupervised learning generalizes better. And we also show these results for CIFAR 10. And I think the reason behind this is that when you're learning unsupervised learning methods, you are sort of not just learning class-dependent features. You are capturing more information than just that, because there's no signal for just learning the class information loss, and it's more relying on the minimizing the distortions between views, and that's, I believe, a better signal to learn representations. Then the next thing we wanted to do was again a few shot training evaluation. So these are some things which have not been done in the past continual learning benchmark. So we try this in our work to see how much are we robust to various of the things that we try. The way we construct the future training evaluation is that we evaluate on a limited number of training instances across various tasks. So for each task, you have less number of training instances. And if you see the results here, then the dataset size per task, we reduce it from 2500 to 100. And if you see the SCL, the performance decreases around 30% in absolute numbers between 2500 to 100. And if you compare with UCL, the performance decrease is just around 10 to 15% across all the methods. And the similar thing we observe for forgetting. UCL is much less prone to forgetting compared to the supervised counterpart. So moving from the quantitative analysis to the qualitative one. So these results show that our method works pretty well, but the answer that we wanted to answer was why it's even working well and what are the insights that we can get out of this. So moving to some of the qualitative analysis. So we visualize a loss landscape, and the way we visualize this loss landscape is that you take the first task during various stages of the training. So basically we evaluate the loss landscape of task 0, after task 0, and also after the last task. So let's see the results here. So if you see the loss landscape after task 0, all of them basically look pretty same, because after task 0, if you're looking at the loss landscape, there is technically no forgetting because the model has not seen any other task right now. But if you see it after task 19, you would see that the loss landscape does start getting a little brittle. It's also not as smooth as you have it in task 0, which sort of answers that SCL is normally more prone to forgetting, which is hurting the loss landscape on the past tasks. Now, let's see it with UCL. So if you see with UCL, of course, for T0, all of them look similar because you don't really have forgetting. But if you see for T19, you can see a significant difference between the loss landscape of like SCL versus UCL, where SCL is a lot more stable. It's also flatter and smoother loss landscape, which basically shows that why it's having better lower forgetting compared to SCL. It's mostly more robust to the catastrophic forgetting scenario. And moving from the loss landscape, next we take the visualization of feature space. So we show that we visualize the second block feature representations. So we visualize basically on task T0 and T13 after the completion of continual learning. So we are seeing that how the representations are changing for the past tasks after we have ended the training, and we see it for a bunch of tasks to see that the phenomenon holds. So let's see at SCL first. So here are the visualizations, and the numbers below it are basically the accuracy of that particular method on that task. So if you see the features, they are quite noisy and they do not really have like coherent patterns. So for example, if you see like GSS, or if you see like any of these methods, you can't really get much out of these feature spaces, and it's hard to interpret what the image actually was. And this shows that, yeah, they were prone to forgetting, which is hurting the past task representations. Next, let's see for UCL. So if you see for UCL, all the features, just changing the learning objective, get a lot more interpretable. They are more relevant and they learn more distinctive features in comparison. And as I said before, I think this is because UCL is capturing more than just class specific features, and it captures some information which is independent of the class labels, other like not similar to the supervised one where you're just training on the cross entropy loss and like, biasing yourself towards the class specific information. And if you see here like the mix-up, you can see that the features are a lot more relevant. You could actually interpret that what the original image was in comparison to any of the other methods, which shows that why it was getting more accuracy and low forgetting. And the next thing we wanted to see was, now that we know that it's having better loss landscape, it's having a better feature space, but where is this distinction actually coming between both of these methods? What's the difference between a supervised and an unsupervised method in the feature space? Where do they diverge from each other? So that's when we do the similarity analysis. So what we do for similarity analysis is that we take the central kernel alignment, which is the CLAI method, which measures the similarity between two independent models. So the way we do is you take two independent UCL models, you take two independent like supervised continual learning methods, and you take one UCL and one SCL model, and you want to see how similar are these representations. So let's focus on the red bars first. And if you compare red and blue, basically you would see that the red ones are more similar than two blue ones. So basically what I mean there is that two independent UCL models are more stable or closer to each other than two SCL models. So if you are training both of them independently to separate UCL and SCL models, UCL would be more similar and get you a like better performance, a similar performance. A more interesting thing is to see the difference between a UCL and a SCL model. So if you compare this green bar, you would see that they're quite similar on the lower layer. So for up to layer 3, most of them, like other than DER, has a similar feature representation, but they are finally diverging in the last block. And that basically answers that it's mostly that the final layer objective, that how you train those models, is causing the difference in the learning. And they are learning similar lower block features, but it's the higher layer which is actually diverging. So this might be interesting to investigate in future works, that do we even really need the lower layers to have or prevent the forgetting? It's mostly the final block which is actually causing you the trouble, and we can fix the problem by investigating that further. So coming to the conclusion, so in this work, we attempt to bridge this gap between continual learning and representational learning. We tackle two crucial problems like of continual learning with unlabelled data and representational learning on a sequence of tasks. We show that UCL achieves better performance over SEL, and we show that over a range of tasks, including continual learning evaluation, out of distribution evaluation, and few shot learning evaluation. Then we analyze and show that it is due to their characteristic ability to learn discriminative and human perceptual patterns. This makes them transfer better and basically more robust to catastrophic forgetting. Other than this, we propose lifelong unsupervised mix-up, which further alleviates catastrophic forgetting and learns just on the interpolated instances directly. And we really hope that our work can be an essential step towards building continually learning unsupervised representations and can bridge this gap between both these communities to have better methods. We also release our code online, and there are a lot more results and analysis in our paper, so do check it out. And yeah, I'll be happy to answer any questions. Thank you.
Thank you very much, Dian. This was a really nice talk, a really nice work. I really enjoyed also reading through the paper, and so yeah, I actually have many questions, but let me just start with one, and then maybe also James, since you're here, you can check on YouTube and just tell me if there's some questions also from our viewers on YouTube. And I can also check actually the chat here so that we can all see the questions coming. Anyone feel free also to open your mic if you want and ask questions. So maybe just a clarification on the evaluation of the supervised methods you compared to. So do the supervised methods use the KNN also for classification, or do they use like a linear classifier trained on the labels?
So that's a good question, and we use the KNN classifier for both of them. The reason for choosing that was that we wanted to see the forgetting of the representations in general and not be influenced by the final layer. Okay,
thanks. So if you can go back like to the table of the first table of results, I was pretty impressed to see that actually the naive fine-tuning is like achieving a very good performance, right? So we are used to see naive subjected to complete forgetting, so like going back to chance level for previous tasks. So what does this mean is that basically if you remove the forgetting of the last layer, the classifier layer, you remove lots of forgetting while still being able to achieve a decent performance, not a good one, because I mean you're not training a classifier, so of course you lose something, but I mean in the end you gain with respect to the fine-tuning we are used to, at least with single-headed models, right? So is that correct, or do you have other opinions?
So it depends. I think just removing the last layer won't really help. Like if you see the supervised learning methods, we do remove the last layer and take the KNN classifier for evaluation. It's more about how you are learning those other block representations. So the problem with the supervised one is that you are very much focusing on your task representations by having those class dependent information. But for unsupervised, you don't really have that particular objective when you are learning, and that's I think the reason that basically provides you the gain.
Yeah, that's true. But still, I mean, it's quite impressive to see a fine-tuning achieving 60% on split cipher 100. So, I mean, continual learners out there, just drop the classifier and use a KNN if you want to show a good fine-tuning. But joking aside, I can ask a few other questions, but first I just wanted to make sure that no one has questions in here or on YouTube. James, can you confirm this?
Yeah. There's no questions on YouTube at the moment.
Okay, great. So coming to another question, which is actually related to this, right? So to the KNN. I was wondering, in KNN, you are like storing the entire set of predictions for the dataset, right? In order to do the matching of the test time.
Mm-hmm.
Okay. So do you think that since it's working really well on average, also without any continual learning technique to use KNN, what do you think is the limit of scale of KNN usage for real world problems in which, I mean, if you think about maybe NLP or even large computer vision datasets, this is quite hard to do, right? So is this, do you see this more as a way to probe the representations built by the unsupervised and self-supervised learning, rather than a practical applications then in which you can just train your model and then use KNN really at inference time?
Mm-hmm. So I would still not say that it would be the KNN which would be the gain. So for example, if you use a linear classifier for fine tuning on each of these tasks, I believe that should give you better performance than using the KNN. But it would be that the representations which are learned beyond this linear classifier or the KNN that you have, those are more robust to forgetting. And
okay,
talking about
so do you think that training a linear classifier is going to give you like similar performances with or even better with the ones reported here?
I believe it should be better because in that case you are explicitly training for the task. So that's what the self-supervised learning methods normally also do. They do both KNN and linear classifier evaluations, although the trends do hold across both of them. But since in linear you are specifically targeting for that particular problem, you might get more gains than what you have using a KNN.
But shouldn't there be forgetting on the previous tasks if you train a linear classifier? Like, I mean, the standard naive fine-tuning in continual learning with a single head, of course. I mean.
So the linear classifier that I am mentioning here is that done for each task separately. It's not learned like across all the tasks.
Okay, yeah. Then
so you don't have the forgetting there.
Yeah, that's true.
And answering your second question about the scalability of KNN, so you don't need really the full data set in the memory bank. So the method that we are using for our work all shows that you can use a subset of that data space and it works pretty well. And this is also the method which has been used for all the representational learning methods to my knowledge when they are doing the KNN evaluation, and it does scale to like ImageNet and other large downstream task evaluations that they do. So I do believe it's quite scalable.
Yeah, that's cool. I didn't know about that. So this seems really useful for continual learning. And what about the replay memory size? So more or less, which is the size of the replay memory for LAMP?
So we use the size of I remember 200. We do mention the sizes explicitly in the paper. What's the replay buffer size, and we use it the same across all the methods to have a fair comparison.
That makes sense. And I was just wondering about the applications of this approach, which I mean seems really effective, to other related to unsupervised, but maybe there's space to work also on semi-supervised continual learning, right? So you can, if you have labels for few patterns, you can train a linear classifier or use, some statistical, more statistical oriented classifier just to mitigate forgetting, and then use these powerful self-supervised methods to learn continuously from the unlabeled patterns, right? So do you think that's a good option, or do you already have something in mind for this?
Yeah, I think that's a good question. So depending on how you are using the labeled instances, so I think that's what determines the whole fate. Like I'm just curious, like if you do have the labeled part in the training first, and do you have forgetting at that point of time once you are done with training of the labeled instances, and then you are plugging in your unsupervised training? Does it improve the forgetting? Does it lower it? Like how does that combination work? Like I think that would be an interesting thing to investigate.
Yeah, great. So do we have any questions from here? Otherwise we can thank Vivian for the presentation. Okay.
I just wanted to say thank you very much. Enjoyed this work a lot.
Yeah, thank you very much.
Yeah, I second this. It was really nice and refreshing talk. So thank you, Divian, for being with us today, for the nice presentations, and thank you everybody for attending the talk here and on YouTube. We have this every week, so feel free to join also next Thursday for the next ContinualAI seminar. Have a nice weekend. Bye bye.
Have a nice weekend. Bye.